Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, we're happy that today our very own Alexandra Kola will tell us about unique games. You've seen all the cakes in honor of this before. Anyway, please.
Hello. Let's see. We have two devices for the talk, one remote and one pointer. Okay. So I'm going to talk about unique games. Probably most of you have heard something about unique games, but a lot of you might not know, so I'll explain hopefully everything and give you some algorithms about them. Okay. So let's start with a problem that you hopefully all have heard of. Simple problem, the Max-Cut problem. You're given a graph, G, and the objective is to partition the graph into two parts such that the number of edges that cross the cut between these two parts is maximized. That's the Max-Cut problem. Okay, so long time ago, Carr proved that this is an NP-complete problem, so there is no hope we can solve this in polynomial time unless p equal to NP. So the next best thing to ask what to do with it is to approximate it. So what about approximating Max-Cut? There have been several approximation algorithms in the literature, starting with a kind of folklore knowledge that a random cut achieves a ratio of 2, so it's at least as 1/2 of the optimal. And then in a breakthrough paper, Gemans and Williamson at 94 showed that there is a 0.878 approximation algorithm for Max-Cut, and they use this very exciting convex programming technique and rounding of the output of the convex program, and they were very excited about it. And this ratio is something that comes out r cos of r over pi, 1 minus r over 2. So it's a very nice formula. Okay, so very nice. Yeah. So how many of you think that this is the best we can do for Max-Cut? It's simple. 1, 2, 3, 4. Sorry, I have 3 arms. Okay. Yeah, no, we only have 4 people that think that this is the best we can do. So.
What do you mean that exists? What do you mean we can do? That's known or that's possible?
That's possible.
Okay.
So you vote yes or? Okay. So very few people think that this is very nice. Quantity is the best you can do for Max-Cut. However, if unique games conjecture is true, that is the best we can do. And in fact, this is not a coincidence. Unique games conjecture is a tool, basically, that captures exact inapproximability of many important problems for computer science like Max-Cut. So as you see here, unique games conjecture hardness is exactly matching what we can do algorithmically for Max-Cut. Similarly, for Vertex cover, we have an approximation algorithm of factor of 2, and we cannot do better. Similarly for Max-K CSP. So you see that this is amazing. I mean, this seemingly unrelated thing proves exact approximability of several problems. Okay, so let's see what I'm going to talk about today. I'm going to tell you what is this unique games conjecture. Then I'm going to give you the connection between unique games and graph theory, and hopefully manage to present the proof that unique games conjecture is false when a graph is an expander, and some other cases as well, and then end up with some open questions. Okay, so let's start with the unique games conjecture. So this next slide basically is based on research of one of my collaborators, Yuri Makarychev. So unique games, what are unique games? Unique games are popular not only among computer scientists. In fact, if you search at Bing, you can see like 70 million pages about unique games, and you can play unique games in arcade or.
70 million have the phrase unique games, or just the two words. unique
That's the
games.
searches that say, when here
Yeah, that's
says,
different.
yeah.
It's
Uh,
not unique games. It's the word unique and the word games.
What? Okay. Okay, but a lot of them have unique games as like a phrase, and this is one example. Moreover, if you search at Yahoo, you can see that you can purchase unique games online. So that's very nice as well. And if you search at Google, you can see that unique games might have something to do with the unique games conjecture. So, okay, but unique games for us now, for the rest of the talk, is going to be relevant to the unique games conjecture, and this unique games is a unique label cover problem. So you're given a set of constraints. As a simple case, which is as hard as a general case, assume that you're given a system of linear equations modulo some prime k of the form xi minus xj equals cij mod k.
You said K was prime?
Yes. And k is called the alphabet size. So is there any question? And the goal, unique games, is basically to find a labeling, an assignment of 1 through k to xi's to maximize the number of constraints that are satisfied simultaneously. Okay, let's see an example. Say we had k equals 3, and we had x1 minus x2 equals 0, x2 minus x3 equals 0, x1 minus x3 equals 1. That's an example of a simple unique game. And you can see it as a graph. It's just equivalent representation, the constraint graph. So you put one vertex for its variable, one edge whenever there is a constraint between the variables, and you just put a constraint on the edge. Okay, so this would be the graph that corresponds to that instance. And let's see an example of an assignment. Assume that I assign 0 to every single variable. What does that mean? It means that this constraint or this edge is satisfied, as well as this one, but not this one. And in fact, that's the best I can do for this game. So the value of this game would be 2 over 3. So, that's the idea. That's what unique games is. And I'm going to explain unique games in terms of deregular graphs for simplicity for this talk.
So what's unique about this? Is it that there is
The one-to-one correspondence. Yeah, that's a good question. It's the one-to-one correspondence that if you assign one variable to one value to x1, then you only have one.
two variables?
Yeah, so it's a permutation basically between. In the general case, this can be any permutation, not just linear equations. It's just simple. Yeah.
But the k is fixed. You're not playing with k.
An instance is given along with k, yes. So when the graph is given, k is given, the instance is given. Okay, so that's what are unique games. Everybody clear?
Why then came? That's
Because you can buy it online, you can play, Okay, so no, okay. So it's a game because, historically, basically, it came from two-prover, one-round games. So in computer science, complexity theory, we have this. We like thinking of equations and relations between variables as having a verifier and one or two or multiple provers. And then you model, if verifier asks questions to the provers respond back. And you can model each answer of the prover as taking, map it to 1 through k, one value. And then you put a constraint that the verifier accepts if, the prover sends these 5 values and rejects otherwise, and that's the constraint. And if this is unique, so one-to-one correspondence, this is a unique game. So I don't know if that's, but I don't want to get into the history of that right now, yes.
The edges are also labeled with the 0 or 0 or 1 and so on, right? So x1 minus x2 is 0. So that's a label on the edge.
Yeah, you can think of it as a label on the edge. This is not the graph I'm going to be using mostly, so it's going to be more clear in the future of the talk. Okay, so what is the conjecture now? Khot in 2002 conjecture that given an instance of unique games with actual value 1 minus epsilon or greater than 1 minus epsilon, it is NP hard to satisfy even a delta fraction of all the constraints. So in fact, basically, to be more accurate, it says that there is a sufficiently large K that if you give me an epsilon and delta, I have this hardness promise. So
I don't understand. You started with saying given an instance, that the conjecture isn't about any particular instance.
no, but the conjecture says, okay, you give me an epsilon and a delta, and I give you an instance that has large enough alphabet size K, such that it can't be hard to distinguish between these two cases. So it's parameterized by...
A particular instance, it doesn't make sense.
For every epsilon and delta you give me, I give you a different instance.
Yeah, I'm confused about the order of the quantifiers as well, because you start off with given an instance. So which...
This is more rough. I mean,
Yeah, we're asking you to state it clearly. So
that's what I'm stating clearly.
No, but it didn't make sense. If you're given epsilon and delta, and then you're given an instance, it can't be hard to distinguish in a particular instance.
Sequence of instances.
I'm not sure I understand the question.
So for
Can
every
you write
epsilon
down on the
and
board
delta-
with all the quantifiers?
So for every epsilon,
For every
there
delta.
exists a K, such that the unique instance with alphabet size K is
Such a what?
the unique instances with alphabet size K is that we distinguish between.
Okay.
So is that? Yeah. Oh, sorry. Should probably write it more. Okay. So as we saw before, it implies that many known approximation algorithms like Max-Cut, Vertex cover, KCSP are optimal if Unigame's conjecture is true. And in fact, Raghavendra 2008 in a breakthrough paper proved that for CSP problems, semi-definite programming is the best you can do to approximate them, assuming the Unigame's conjecture. So there is this deep connection between semi-definite programming and Unigame's. So is Unigame's conjecture true? That's a major question. And note that by the definition of the problem, this is kind of embarrassing to not know if it's true or not, because we are able to solve system of linear equations exactly in polynomial time. So asking even to approximate them by really distinguishing 1 minus epsilon to delta, we don't know how to do. So that's kind of shocking, at least to me. So in fact, people have worked on it and thought about it for a long time, and there have been several attempts to prove or disprove the Unigame's conjecture. So disproving, well, you have to find an algorithm. So the best known polynomial time algorithm is due to Makarychev. And in fact, Khot and Vishnoi showed that this cannot be improved by semi-definite programming. So a particular method of attack of Unigame, semi-definite programming, is doomed to fail. And in fact, Khot, Kindler, Mosel, and O'Donnell showed that if you improve this algorithm beyond the parameters that Makarychev have, then you would refute the conjecture. So
What is the running time of this algorithm? So trivially you can do 2 to the epsilon then.
it's polynomial time.
What's called?
So this is, I'm talking about efficient algorithms now, and then I'm going to explain more about other algorithms. I mean, in particular, if Unigame's is NP complete, you can always solve in exponential time. Okay, so and there have been attempts to prove the conjecture, maybe with strong parallel repetition. Maybe you can reduce a gap max-cut problem. You can't see that, right? It's not, yeah. I don't know why. Yeah. Yeah, it shows better on my laptop, but yeah, I'm sorry. Okay, so I'm going to read what it says and say what it says. But basically, there have been attempts to reduce problems to Unigames to say, to get a feel of like maybe Unigames is hard. And one hope towards this direction would be to, reduce max-cut, a gap instance of max-cut to Unigames by using strong parallel repetition. I'm not going to say much more what that is, but the point of this is that Raz 2008 showed that this is not possible. So this attempt to prove the Unigame's conjecture failed. And okay, let's now, since we can't prove or disprove it, let's see what are hard or easy instances, if we can show anything. Since all these several attempts have been around, but there is still no consensus about it. Maybe some intermediate steps that could help us, decide or get an intuition about what's happening. And towards this direction, there have been, people have studied expander graphs and local expander graphs, including, joint work with Aurora, Khot, Tulsiani, Steurer, and Vishnoi, and Tulsiani, and then local expanders Aurora and Pagliazzo, Matthews and Steurer, and then Steurer, Raghavendra. So now we know that these graphs are easy. There are polynomial time algorithms that can solve unigames on expanders and local expanders.
You didn't state for me how is the graph related to the problem yet?
Not yet. I will. That's the second section. Okay. And then has been another line of research that said, okay, maybe let's relax my polynomial time requirement a little bit and allow for slower algorithms, maybe quasi-polynomial or sub-exponential. And in fact, for a few graphs, there is a quasi-polynomial time algorithm that solves unigames on those graphs. In particular, the class of graphs that are hard for semi-definite programming are solvable. And this is a paper of mine last year. And then a breakthrough paper of Arora-Barak-Steurer showed that for any graph, you can solve unigames in sub-exponential time, which still doesn't disprove the conjecture. There are hard problems that have sub-exponential time algorithms. And then towards proving, maybe we can find distributions. Maybe it's easier to argue about distributions that are hard. But it turns out that at least for random instances, the answer is no, because random graphs are expanders, roughly. And then for quasi-random instances, I know you can't see that, I'm sorry. For quasi-random instances, a recent work by myself and the two Makarychevs, we also show that quasi-random instances are easy. So there is this is also failing as a direction. Okay, so that's the state of the art, and here is a summary of the algorithms that run in polynomial time for general graphs and approximate highly satisfiable instances of unigames with parameters that depend on either the alphabet size or log n. So these algorithms are all dependent asymptotically by the alphabet size or log n. And in fact, they're all based on semi-definite linear programs.
What's the right-hand column?
On 1 minus epsilon satisfiable instances, the algorithm finds an assignment that satisfies that many constraints. So if epsilon is tiny, then that's constant, that's good. But if epsilon is relatively some constant, then if epsilon is bigger than 1 over log k or 1 over log n, then this gives nothing. And in fact, this is the best, the algorithm I was mentioning before, that if you improve the parameters of this algorithm, then you would have refuted the unigames conjecture. And it's tied for semi-definite programming. And then for expander graphs, with the people I mentioned before, plus the Makarychevs lately with improved parameters, on 1 minus epsilon satisfiable instances, we can recover constant assignment that depends on how good of an expander the graph is. And similar for local expanders. So the grouping, the similar thing about most of the approaches here is that, as I said before, they're based on semi-definite or linear programming.
What do you mean by constant?
A half, say, or...
Oh,
it depends on the expansion. But the interesting case is when it's bigger than delta, so you have to...
Right.
And all these are polynomial time algorithms where the exponent depends on epsilon?
Yes, these are polynomial time algorithms.
And to the function of epsilon, right?
Yes. Okay, so the thing that to note here is that these algorithms all depend on convex programming, semi-definite programming or linear programming, and lately there is this past year on a result of mine. There was this algorithm that solved unigames with completely spectral techniques in graphs that had few large eigenvalues, say, or graphs with a certain spectral profile. So this is different in that sense with the previous algorithms. And also it solves in quasi-polynomial time that instance that was tight for the semi-definite program. And then this recent year, ABS gave a sub-exponential time algorithm and used this algorithm of mine in the paper. And as I mentioned before, we have these semi-random instances that are easy. So this is what the picture is for unit games. This is the state of the art. And let's now go and see all these graphs that are related to unit games. Do you have any questions so far? So here was the constraint graph for this particular set of linear equations that I mentioned before. So we can see unit game as a constraint graph. We can also see it as another object that's called the label extended graph. And the label extended graph basically goes as follows. So for every original vertex of my graph, which was a variable in my set of linear equations, you replace it with k vertices. And then every edge, you replace it with a matching that matches the little nodes here that satisfy this constraint. And you do that for this edge and that edge and this edge. And that's the label extended graph. Is that clear? And this is a graph. It also has an adjacency matrix, which is nothing but the original adjacency matrix of the graph with each vertex replaced by a block with the permutation, the constraint that sits on, between this vertex and neighbors. Okay. So that's the label extended graph. That's the representation of this label extended graph that I'm going to use. And let's try to use that now to show that unit games conjecture is false on expanders. Okay. So we have this constraint graph, and now assume that this constraint graph is an expander graph. What do I mean by an expander? How many of you have heard the no expanders? How many of you don't? Okay. So expanders basically, I can define edge expansion to be a ratio of the number of edges crossing the sparsest cut over the one side of the cut. You can think of it as just a quantity that shows you if I see the worst possible cut, the sparsest possible cut in my graph, how can I quantify it? So edge expansion is just the minimum of the ratio of edges over the one side of the cut. And then there is a spectral representation of expanders that you can use the second eigenvalue, second largest eigenvalue of the adjacency matrix of the graph, which is just the max over all vectors perpendicular to the all ones vector of the quadratic form of my adjacency matrix over the norm of the vector. Probably if you've never seen expanders and eigenvalues before, this is not very helpful, but I hope that for the rest of the people this is helpful. And expander graphs, if you look at the spectral gap, the difference between the first eigenvalue and the second eigenvalue, expander graphs have large spectral gap. And a lot of edges cross every cut. So for large spectral gap, a lot of edges cross every cut, these two quantities are kind of indistinguishable. And the relation between them is given by Chigger's inequality, which basically says exactly that, makes that connection precise. So for us, you can think of it as some constant, spectral gap, and expansion would be also some constant. For other values of it, it's not a precise relation, but for constant it is. So are you clear what is an expander graph, roughly? Okay, so let's assume now that my constraint graph is an expander graph in that sense that basically the lambda, the spectral gap, is large, it's constant. And remember, we're talking about D regular graphs. You can think of D as some large constant or log n or something like that. And the result that appeared in a joint work with Arora-Barak-Steurer, Tulsiani, and Vishnoi and a manuscript with Tulsiani, we saw that when a unigame's instance is highly satisfiable and the graph is an expander, a spectral expander, then there is a polynomial time algorithm that recovers a good assignment, 99% satisfying assignment, a half is good enough in polynomial time. So that's the result, and that's what I'm going to talk about today. But why look at expanders? It is a natural object somehow, but why did we start looking at expanders? Well, as you remember the previous table of exact inapproximability results, if you look at another important problem, the sparsest cut problem, then what happens is that the best known algorithm is given by Arora-Barak-Steurer at 2004, and it's an approximation factor of square root log n. However, even assuming the unigame's conjecture, there is no hardness known for the sparsest cut problem. And that bugged researchers in computer science a lot of time. Like, everybody was wondering why is it the case, and everybody was trying to prove some hardness for sparsest cut. Okay, but since there is no such thing, let's see why. In fact, all the known techniques show that it's unlikely that there is such a reduction from unigames to sparsest cut, because if you start with a sparsest cut instance that does have a sparse cut, and you apply known reductions, usually the instance that you get also has a sparse cut, and that does not depend on whether or not the unigames that you started with had a satisfying assignment or not. So this is true unless the unigames instance you started with had some expansion, because then any sparse cut in the end instance would correspond intuitively to just a good labeling. All the cuts that would originate from the initial graph you started with would not be sparse because the graph is an expander. So every sparse cut you would find here would just correspond to a good labeling. So there was this off-the-record belief, which was made more precise by a manuscript by Khot and Vishnoi, that showed the hardness of sparsest cut, assuming unigame's conjecture is hard on expanders. There was this off-the-record belief that expanders were the hardest instances, in fact. However, as we know now, this is not the case. And let's see why. Sorry. So the proof that I'm going to present today, we have two proofs, one with semi-definite programming, one with spectra. I'm going to present the spectral proof. It's probably nicer and more intuitive to present. So we had this label extended graph, which I hope you all remember what it is. And now let's just pick one little node out of this blurb of nodes, exactly one, and take a second and convince yourselves that this set, exactly one node of its big bunch of nodes, corresponds to some labeling, some assignment to my variables from 1 to k, or from 0 to k minus 1, I guess. Okay, so you can also see that as a characteristic vector of a labeling, which is a k times n-dimensional vector that has exactly 1, 1 in its block that corresponds to its vertex and 0 otherwise. And if you remember this big object that was the adjacency matrix of this thing, just for intuition now, let's look at a perfectly satisfiable game. So perfectly satisfiable game, we know how to solve. I'm not saying anything deep here. But observe that this object, the label extended graph, is just k disconnected copies of the original graph. And it's a very nice thing to look at because these characteristic vectors now that correspond to perfect labelings that satisfy all equations are just eigenvectors of this matrix of eigenvalue highest possible, exactly d. So, okay, that's very nice, but I haven't done anything. Well, the intuition here is that a 1 minus epsilon game is almost a satisfiable one in the graph theoretic sense. So it's basically can be seen as perturbing this graph a little bit and then see what happens to the spectra. And that's, in fact, what we use in the proof. So we start with the 1 minus epsilon satisfiable game. Let's go back to our previous example. we can think of it we could do some reverse engineering here. We can think of it as coming from a completely satisfiable game when a malicious adversary picked epsilon fraction of the edges, changed the permutations on the edges, or the equations rather, and now the game became 1 minus epsilon satisfiable, but before it had a perfect satisfying assignment. And in the label extended graph case, from the completely k-disconnected copies of my graph, it would go to something not quite k-disconnected copies of the graph. Okay, so how can we analyze this? Well, as we saw before, these k characteristic vectors of perfect assignments on this perfect game were eigenvectors with eigenvalue d, and they, you can take their span, this k-dimensional eigenspace y of this graph, and there is all the information about the best possible labeling. But now you don't have a handle on that. You don't know that. You don't know where the adversary picked the epsilon fraction of the edges. What you do have a handle on is the eigenspace of this graph. So, okay, let's take the first few eigenvectors of this graph, and we'll see how few we take in a second. So, if you take, say, all the the span of all the eigenvectors with eigenvalues greater than 1 minus 200 epsilon d, sum 200, then it's easy to see, and I'll show you in a second, how all these nice characteristic vectors that we wanted to find have a large projection on this eigenspace. And note that if we knew any of those vectors or a vector that is close to them, then we would be done, because we could just read off the assignment from the coordinates. Okay, so it's basically...
Can you go back to the first one? You said we should think of the 1 minus epsilon game as obtained from a perfect game by changing some edge. But formally the definition is that
you change basically this, you can think of it as changing these graphs in the matrix perturbation theory sense.
And there's a question of whether it's vertices versus edges. That's the only answer.
when you say
It's just edges.
it's edges, it's a proportion of those that are set. Constraint is given by an edge. So, but if something is 1 minus epsilon satisfiable, does it mean that you can actually get?
Yeah, but fix an assignment. Fix an assignment and change it backwards.
Change the epsilon. Right. Okay. Okay.
I mean, there might be a lot of ways to do it, but it doesn't matter, which one. They're all isomorphic.
Thanks.
So, right? So, okay. So now this slide is about convincing you that every Sats vector has a high projection onto this eigenspace, and it's just very simple math. The colors are all wrong, and it's not my fault, as a disclaimer. All these, these colors and what you couldn't see previously. I have different colors in my laptop, but anyway. Not that it matters now, because you can see, but before that you couldn't see. Okay. Yeah. So, I mean, just basically by looking at the quadratic form of this vector, you can convince yourself really easily that it has a high projection onto the high eigenspace, W, of the game that we see, the game that we have a handle on.
Yeah, well, that's because the inner products are close.
I mean, you show that there is a high inner product just because the quadratic form is close. I mean, it's a very simple calculation. Yeah. So if we knew this projection, if we knew this vector that's really close to this nice characteristic vector, we would be done. Because, okay, some blocks of it would be all messed up. We forget about them, but we could still recover a 90% assignment just by reading off the good coordinates that are close to those ones. Because these two vectors are close in L2 norm. Okay, but how are we going to know this vector? I mean, we know this eigenspace, but I mean, it's kind of like looking for a needle in a haystack. Look for a vector in an infinite cardinality set, basically. The set W has infinite number of vectors. Okay, so yes, but how do you find a particular vector in that space is the question.
So in which eigenspace are you looking?
This W, which is the eigenvalues larger than 1 minus 200 epsilon d of my own, the game that I see.
The span of eigenspaces. Not one.
Yeah, this, I use eigenspace sort of abusively in the sense I mean the span of all eigenvectors. Okay, so I mean we are searching for a needle in a haystack, but we can do it sort of efficiently if we take a net. You take an epsilon net of the subspace, so you discretize it, and you look at every single point on your net, and then one of them is going to be close to my vector W that I was looking for. And then, I can do the same, maybe lose another epsilon, and read off the coordinates out of each block and recover the assignment just by looking at what coordinate is maximum in each block. Yeah. And observe that the running time of this algorithm is just exponential in the dimension of W, just because you take this epsilon net, and that's the bottleneck. Mostly. Okay, so let's see for expanders, what is the dimension of W for expanders? Ideally, if that dimension was really low, constant or log, then we would have a polynomial time algorithm. And in fact, that's what's happening. So remember that the spectral gap was this difference between the first and second eigenvalue of the expander. And we had these two subspaces here. In fact, for expanders and such games, you can show the spectral gap is the same for the label extended graph. So in a more generalized sense, and I'm not sure why this is not showing either, but this was high. So Y now is a k-dimensional space that contains these k characteristic vectors, and you can show a similar spectral gap between Y and Y perp, the complement, and then you can basically see W as a perturbed analog of Y. And things are easy for us after this observation because long time ago, people that are expert in matrix perturbation theory, Davis and Kahn, were able to show that if that is the case, then the angle between Y and the perturbed version of Y, which is W, is small. And after that, you're done. Basically, you show that for every vector here, there is a vector in Y that is close, so the dimension of W cannot be larger than the dimension of Y. Okay, so, this was a general algorithm, like a black box algorithm that we plug in expanders. We observe that, or rather we prove that these dimensions are bounded by K, and K is log n. It's enough to consider K log n by the statement of unigames. It says that there's a large enough constant that depends on epsilon and delta. So if you take K log n, it solves all your problems. So the running time is 2 to the K, which is 2 to the log n at most, which is polynomial n. So that's the algorithm for expanders. Any questions? And in fact, you can go one step further and say, okay, let's plug in other graphs there. Let's start with this Khot Vishnoi notorious graph that was proved that STP fails there, and you cannot hope to do anything with semi-definite programming due to this graph. It turns out that, if we look at the corresponding eigenspace of this graph, then it's polylogarithmic dimension, so the algorithm would be quasi-poly. Not exactly polynomial time, but almost polynomial time. And you can apply this algorithm to other graphs of your choice. And that's the proof.
But you need a separation. You need a gap.
I'm sorry?
You need a spectral gap for your...
Okay, this proof is not exactly the same. It's not identical. So you have to prove a lot of other things to obtain an equivalent result. You don't use the sine theta theorem as is, but it turns out that it's similar. And then that concludes my talk, except for open questions. So if you have any questions.
The Vishnoi graph, is that hard to describe?
So the graph is basically a quotient of the hypercube by the Hadamard code. The instance, it's a little more complicated. I mean, what permutations you would put. The point there was that the spectra of Kelly graphs, in the label extended graphs of Kelly graphs, have spectral profile that scales k times the spectrum, roughly. It scales like k times the spectrum. So there are k copies of each eigenvalue roughly. So you can bound the eigenspace of the instance with the eigenspace of this Kelly graph. But then it's just characters and you understand.
Another question. So using this polynomial algorithm, can you break the Gomez-Williamson bound for like special classes of graphs, for example?
So what was your question?
So if you use, so kind of going back to Maxcat, for example, right? Can you use the techniques here to design better algorithms, better Maxcat algorithms?
I haven't tried, but I think
there's no obvious reason why it should work, but
there's no obvious reason why it should or shouldn't, but yeah. So okay, let's see what's open in the area. We'll disprove the Unigame's conjecture. In the meanwhile, though, maybe you want to think about something easier. So what about other special graphs? What about the hypercube in particular? The hypercube is a very easy to describe graph, just the Boolean cube, 0, 1 to the n. And the problem with the hypercube is that every known approach fails in such a simple graph. In fact, the spectral approach that I presented before gives sub-exponential time, which is the best we can do for any graph anyway. And we basically don't know what's going on. And I mean, I think Subhash himself asked this question first, so I don't want to take credit for asking it, but that's a good question that I'm interested in. And then how do you compare? So for those of you who know semi-definite programming, there are these canonical ways to strengthen semi-definite programs, and they're called STP hierarchies. How do you compare spectral techniques with these higher rounds of semi-definite programming and not just the one that we know that fails? And then, like, what is the best we could do for general graphs? For now, we don't know exactly what's the bottleneck of this approach. And hopefully improve it by searching more efficiently than just taking brute force epsilon nets. Yeah.
So what do we know about the average case hardness of this unique games problem? Is there a
I am assuming that by average you mean...
is there a polynomial time sample distribution for which instance?
What I said in the beginning, actually, was, that we know that these instances are easy. So with high probability, random graphs are expanders.
So you can...
Therefore, you apply the expanders. And a very new result that's not published yet by myself and Makarychev's show that even if you have some sort of randomness, like if you say have a fixed graph and you fix a perfectly satisfiable assignment and then you randomly choose epsilon fraction of the edges to change them, or you do some other step at random similar to that, then it's also easy with high probability. So
this is like this planted...
it's sort of like a planted.
So that doesn't work either.
So that's also in polynomial time.
No other questions? Let's thank Alexandra again.